Yes, I know. The title for this video is quite a mouthful, to say the least. But here it goes. In this video, I will present to you a STEM lesson designed around the 7 E's. 4. Engage. Elicit. Explore. Behind my head. Explain. Elaborate. Extend. And evaluate. What is the actual learning objective? Students will design and create bioinspired wind turbine blades and evaluate their efficiency. What are the student objectives? Students will research how wind turbines function. They will then investigate the various forms of marine organisms which move through water, like the 4 that you see on this slide, and terrestrial organisms which move through air to help guide the design of a small-scale wind turbine blade. Next, students will determine the efficiency of the blade design based on voltage output and the blade's mass and assess additional variables that could improve their wind turbine function. Okay, next slide is going to be a bit busy. Finally, students will evaluate the relationship between the mass and shape of the wind turbine blade and its efficiency. So who is the targeted audience? This STEM lesson, which centers around the concepts of energy and matter and provides students with the opportunity to design solutions to a key engineering problem, can be taught as part of the physical or life science curriculum in middle school. It can also fit in any of the high school science and engineering classes. How long does the STEM project take? Good question. You can adapt this lesson to whatever fits your curriculum needs, but be prepared, as it shows at the bottom of this educator guide, for it to take up to 4 class periods. If this all sounds like a bit much, don't hit the stop button yet. But let's bring back the dynamic humpback whale, because this activity has proven to be quite rewarding for both teachers and students in terms of the provided creative opportunities and the learned concepts which are centered around climate change. Access to this lesson, the associated handouts, and sample data are all provided in the description below and at no charge to you. You're welcome. I should emphasize that this lesson was developed in collaboration with several excellent New York State Master Teachers from the Central New York region and was funded through a grant from the Office of Naval Research to support this Community of Practice project. Let's start with the student lesson slides that I created and kick off with the first of 7 E's, engage. Engage. What is the design challenge problem? So I basically start this lesson by introducing the students to the mobile devices that they have access to and that they could actually use during their classes, whether it be a Chromebook, their own laptop, possibly be a phone, and of course all these mobile devices need to be recharged. So what might be the energy sources to give that charge from the electrical output? So the key renewable energy source that we're focusing on in this lesson is the wind. So the design statement is therefore as follows. Design a small-scale wind turbine blade that would respond to our variable winds to efficiently generate enough electricity to power a class set of mobile devices. And what can we learn from animals, as I showed you earlier, which move through either air or water, that would help make these blades more efficient, more effective? Okay? That brings us to the second of the 7 E's, which is elicit. How shall we guide students to dissect the design challenge problem using open-ended questioning? So some questions that come to mind might be, what makes a good wind turbine? Or where else do we see such spinning blades, as you can see in these 2 pictures from the Naval Sea System commands? So we have created some STEM notebook slides to go along with this lesson. And the key questions that they will start off with answering is what is unique about the shape of a propeller blade, how are propeller blades different, again, which animals that move through water may inspire your design of a more efficient blade. Are there any other examples of forms in nature that could make wind turbine blades more efficient? And how can we actually design, produce, and then test the propeller blade model? Okay? That brings us now to the third E, which is explore. What activities and research shall we plan for student exploration of STEM concepts? Okay? So that brings us to the second part of the STEM notebook, where students are actually working in small groups. And the 3 prompts that are given to them are the following. What are the similarities and differences between animals that move through water and animals that move through air? What unique adaptations do animals that move in fluids have to make them more efficient? Of note here is the flipper of the humpback whale, which shows these interesting bumps, which are called tubercles. And it might help the humpback whale to move its flipper through the water, thereby catching its prey more readily because it reduces drag. And then the last prompt is, can we apply the form of a flipper moving through water to the form of a blade moving through air? Again, with a hint of a 3D blade shown in this bottom picture that has those similar tubercles at the bottom. Okay, another thing that we inspire students to do is to then go on and continue with an actual drawing or drawings, hopefully, of their blade design, prompted by their group discussion. And that brings us to the explain portion, the 4th E. Explain. How can we help students share their understandings from the explore experiences that I just went through and check for any misunderstandings? So we go back to now explaining what is efficiency, how to define this term, how do we calculate it? And then the other thing that we have to focus on is the next step, where we're going to elaborate, which brings us to the 5th E. Got to make sure I'm counting that correctly. What engineering design process shall we use with our students? Okay. So you're seeing here several slides that basically help you with the setup of this STEM lesson. The needed supplies, and I'll only highlight the key ones here. The first one being the wind turbine apparatus, which you've already seen, but I'll show it to you again in a little bit. And then the second thing that you would need is the actual plastic, the moldable plastic that can be used to design the actual blade and create it. This video helps you to actually set up that windmill and explain how to assemble it when it comes in as part of a kit. And the first step that the students can then do as part of this elaborate part of the 7E lesson is to do a baseline activity. What's the purpose of the baseline activity? Well, they're going to use not their own designed blades, but they're going to instead use the control blade that comes with the kit, shown here in the 2 pictures. And what they're going to do is assess the relationship between the distance in centimeters between the actual windmill base and the blow dryer that you can see on the left, and the voltage output in millivolts. Okay, and so they're putting these 2 further and further apart, and obviously what should happen here is the voltage output should decrease as that distance increases. So next you're going to see the STEM notebook again. We're now on the 4th part of that STEM notebook, where they're collecting their data. Now that can be done as part of the STEM notebook, whether it be in Google Slides or as part of a Google Doc. Optional is to do it simply in Google Sheets, because that allows you to immediately show it in graph form. You can create a chart after collecting the data. Okay. So after that, they will actually create the design that they've made. using the moldable plastic. So here are the steps that actually show you how you can actually create, using that moldable plastic, the design. And it's also shown in the video. So the design testing then follows, where you're using a control thermal blade. So this, and I will show you that here, is the actual plastic that has not been molded yet. So this is the plastic the way that it comes. And after molding that plastic using warm water and their actual design, so that they might have to cut out some parts, you can come up with a rudimentary design like this one, which shows you those tubercles that I was talking about earlier, bioinspired by the humpback whale. And you can follow the same test with the hair blow dryer and the windmill at a certain distance, in this case 50 centimeters. The one on the right, slightly hidden by my head, is at the same distance, and then you see here the voltage output. Okay, so they will actually test their design in that regard. And they will record that data in a special data table for that. So once they've done their design testing, they may want to consider going back and forth. How could they adjust their design? Is there maybe a better shape that would make the voltage output better compared to their original design? So key is really to go back and fine-tune that. Of course, they have to record all their work, and again, that can be done in the Google Doc, the Google Sheets, or Google Slides, all available in the description below. So this shows you that actual Google Doc form. So that brings us to the extend portion. So the extend basically refers to what connection to other real-world problems can we provide to our students that can reinforce STEM careers. So to really drive this home, the STEM notebook contains now additional questions with all the resources available. And the questions include, what are the wind turbine components? How do wind turbines work? Are there existing small-scale wind turbines in use in Central New York? And since this lesson was developed in that region, we're focusing right now on that Central New York region. So we have some additional information here to help answer with these questions, such as how do small-scale wind turbines compare to large-scale wind turbines? Because the whole idea is really to upscale their small design to larger scale wind turbines. But then you have to keep in mind, what is the actual wind capacity, in this case, in New York State? And then is there a correlation between the speed of the wind and the location of these actual wind farms in New York State, or wherever you decide to choose to do this? And that brings us to the final E number 7, which is evaluate. So we have an extensive document that goes into great detail how to evaluate this lesson. I'm only showing you a small component of that document, which revolves around seeking and selecting appropriate information resources. And what you're noticing here is that's leveled at 4, 3, 2, and 1. 4 being if the student actually uses enough of these legitimate resources to help guide them through this lesson. And number 1 would be the fewest. And again, this is an extensive document that goes deeper into all the 7E components of the actual lesson. So I want to end this lesson with showing you again the various resources that are available at the bottom of this video. It includes the Educator's Guide, which tells you in detail how to actually construct this lesson, how much time is involved, the standards involved, etc. It also includes the STEM notebook, whether it be in Google Docs or Google Slides form, and a Google Sheet with sample teacher and student data and empty student data where they can collect their work. And obviously also videos that help you guide the process throughout the lesson. So thank you very much for watching en thank you for subscribing at the end of this video. Bedankt voor het kijken en tot ziens.